So we start from this loss landscape question, and the question about that. Okay, so we are optimizing like highly nonlinear function, which is neural network. Are the local minima, are they a problem? So is it going, if you do gradient descent, is it going to get stuck in some poor local minima? Should we worry about that, or what should we probably do something about that? And there are the first thing to understand about the local minima is that some of them arise as a result of the symmetries. For example, we have this permutation symmetry in multilinear perceptron networks. So if we swap this neuron with this one and like swap the weights together with swapping these neurons, it's apparent that we will get the same network, right? But it will be in a computer, it will be a different parameter vector. So the red weights will be in the positions where the blue were, and the blue were at the position where the red were. It will have exactly the same function, right? So for any input, it will predict the same thing, but technically it will be like a different point in the parameter space. So such symmetries would inevitably create multiple local minima, and this is maybe an example of some function that has such symmetries with respect to the flipping of these coordinates. And we clearly see that that's not our problem. So even if there are multiple minima due to the symmetries, we don't care. I mean, all of them are equivalent because they are representing the same function. Yeah, so that's one kind. And the other kind comes from that, okay, so if you have, especially if you have like in the machine learning, we have a sum over the training set of some loss functions. Even the loss functions could be convex, but our predictor is a neural network. It's not convex. So we are summing a lot of functions, and each of the summands may have multiple local minima because they are nonlinear. And the sum will have even more local minima. So this in principle could be a problem, right? But this problem somehow is not as severe as it may seem if you look at the how it manifests itself in higher dimensions. So let's recall what is the local minimum. So local minimum is kind of, there are stationary points, and the thing is that our algorithms will be, we will always looking for gradient descent directions, and if we are in a stationary point where the gradient is 0, then we kind of getting stuck in that point. But in 1D, we have not so many kinds of these stationary points, so some of them could be local minima, some of them local maxima, and there could be inflection points like this. That's also called saddle. And if the function is highly nonlinear, you could expect that there would be many local minima, like this one and this one. I think it's missed from the picture for some reason. But then, okay, if you found this one, we got stuck, right? And that's maybe not the optimum that we wanted. But then in higher dimensions, this picture gets a little bit different due to certain statistics. So like in the 2D, if you look at like second order approximation to the function, we have, or in general in a higher dimension, if you look at the second order approximation to the function, and we can rotate this such that the main directions are our axis, then along some axis the function will be like convex, and along some other orthogonal directions the functions could be concave. So, and depending on whether it is convex or concave in all of these directions. So if it is convex in all of the directions, then it's a local minimum. Concave in all directions, that's a local maximum. And if there are these concave and convex pieces in different dimensions, then it's a saddle point. And these are given by the eigenvalues of the Hessian. So if you write the second order approximation in the Taylor expansion of the function, then here the quadratic form is given by the Hessian of this function, and its eigenvalues determine whether it's going to be convex or concave. So the thing that we are getting is that actually there are many possibilities how this is going to look like. And for this to be a local minimum, you have to have all of these eigenvalues to be positive, right? And then the higher dimension it is, the kind of more chances that one of the directions will be a descent direction. So there are more chances that the more parameters you have, the more possibilities to change the function you have, the more likely it is that there will be some direction in which you still could distend the function. And this corresponds to that. Okay, so actually to get stuck in the local minimum, it could be quite difficult because all of these eigenvalues has to be positive. So there is this, like, okay, let's call the fraction of negative eigenvalues, we will term an index, and if the index is 0, that's the local minimum. So and this will be what kind of quantity we will be looking at. And then there was some theoretical insight coming from theoretical physics. They studied the model of Gaussian random fields, which was somehow relevant to some systems of molecules and such. And they actually derived like theoretical dependence between how far okay, let's look at some stationary point, and let's look at what is how far it is from the minimum, like the difference in this energy or the value of the function from the minimum, and let's study statistical dependence between these, like how far this saddle point is to the fraction of its negative eigenvalues, the index. And the theoretical dependence predicts this, so that actually the further you are, then higher chance that this index, that there are negative eigenvalues, there are distant directions, right? So you have like these statistics. It's maybe curious, it did not occur to me before. This does not involve any dimensionality here for this problem, which is interesting. Maybe a good question. Anyway, like then people wanted to check this on the neural networks, and they like run this experiment, for example. Consider like different configurations of the neural networks in terms of the number of parameters and the amount of the training data. And here on the x-axis we have the energy, and on the y-axis is this index alpha. So here this was like difference between the energies, right? So here maybe it starts from some minimum value, right? And then as the difference to the minimum increases, then now they computed many saddle points, tried to get them exactly, and then they plot all these saddle points into this plot, like, okay, what is the energy versus the proportion of the negative eigenvalues. And it was kind of nicely following this trend, especially around like when this index approaches 0. So this was asymptotic result. So this is like for small values of the energy differences and indices. And here, okay, so maybe here the dependencies deviate, but actually closer to 0, it is nicely followed this trend. And I mean, in general, this is also like not very important which function it is, but what is important is that it's there is this trend that further you are from the minimum in the absolute value of the energy, then the higher is the chance that it's gonna have descent directions. And there are like similar trends measured maybe on some larger networks on some real data sets. So this is here index on the x-axis and the training error on the y-axis. So if the training error is high, the index is non-zero, there are many descent directions, right? So this is what it tells us. Yes, and then there were such experiments like, okay, so what happens if we increase the number of hidden dimensions? So if we go for over-parameterized models, then like, okay, so here in this graph you see the number of hidden units, and then with each number of hidden units they run multiple experiments, maybe 100 or more, and look at the statistics, what is the loss attained by the stochastic gradient descent in that setting. Like, because each run is random, so it could end up in the different local minima or in the different values of the loss. So there are these distributions, and you see that if you increase the number of hidden dimensions, then it is finding the lower values of the objective quite naturally, right? So you increase the model capacity, it could fit the data better, right? But also what you see, it is doing it more surely, right? So here the scatter was quite big, so the optimization was harder, and then sometimes it was getting stuck in this point, sometimes in that point. If we make the model over parameterized, then it is finding the solution that fits all of the training data and is doing it more surely. So this is kind of, we have two advantages from having over parameterized models. Is one advantage is the optimization works easy because of that, and the second advantage is somehow we notice that actually if you do it with this stochastic gradient descent, then, and maybe with some regularization, it actually generalizes also well. So this is like, okay, the current trend to scale up things, get more data, get larger and larger models. So the model size is kind of proportional to the data in some sense, and then let it train. Yeah, so, okay, so this is the summary that local minima rare, and then it's not really a problem in high dimensions, and especially in this mode of over-parameterized models. For like the optimization perspective, maybe we should worry a little bit about different saddle points, because there could be many of them, but they are saddle points are not stable, right? So if you kind of jump left or right from a saddle point, then you will be not in a saddle point, you will have descent only directions. No, how is it? Yeah, okay, so some of the dimensions could be staying as positive eigenvalues, some could stay negative eigenvalues. Like just some of the dimensions could be unstably unavailable for descent. That's the thing. But since we are doing stochastic optimization, this is gonna kind of bump and jump all over the place, and then probably it is enough to escape all the saddle points. Yeah, sometimes this optimization kind of plateaus and gets stuck. So, but I think from this perspective, from this discussion, it is quite unsure that that would be a local minimum. It's just maybe the dynamics of the optimization and interplay of multiple things. So it's actually, in practice, it's really hard, in fact, to certify that you have converged to the local minimum of this optimization of this neural network, because you have lots of this training data, and you have a quite complicated function to check that. But like, yeah, in practice, optimization methods do get plateaued and they do get stuck at some level of performance, and yeah, this might be related to the shape of the function and to the optimizers, but it's not necessarily and unlikely actually that it's the true local minima of the function. Okay, so we go to the next section, where we're gonna spend like most of the time. And
So maybe I'm just like thinking like this, it's plateauing like from this analysis, it looks like it shouldn't happen that often. You should sort of be able to optimize quite well. So maybe what happens is that we don't have sufficient data, and then the loss is kind of, maybe could it be somehow related with not having sufficient data, so not every corner of this loss landscape is sort of covered well, and maybe you can get stuck there, or?
no, I think it's rather related to that we are kind of very over optimistically making a quite large step of this gradient using a mini batch of data, and we expect this to improve. But when it plateaus, that means, okay, so for some data something improves, for some other data it does not, and the size of the step, okay, in some coordinates it might be a good step, but if you do these steps in multiple coordinates all at once, then it is cumulative effect maybe on the function is not as good. So maybe if you like look at the small step size and look at not stochastic gradient, I am sure they will be distant directions. It's just we cannot efficiently make large steps to observe like a big progress of the optimization. Yeah, like this is empirical, my opinion. I cannot back it up really. All right, so yeah, okay. So one challenge this optimization faces is that the dependence on the representations. And we've discussed this already, but let's recall. So what happens? So if you have a function and we look at some reparameterization, so like, okay, so this was our original parameters, and then we say, yeah, let's consider the new parameters which are related by this linear transform. And then let's define a new function of these new parameters such that it would match the original function. So the a w tilde is obviously w back again. So it is the original function. So we kind of represent in the new basis an equivalent function to the previous one. And let's see what the gradient descent is doing. And the gradients are related by this rule. So if the remetrization was having the inverse linear transform here, then the gradient has the like not inverse linear transform. So these are like, okay, so inversely related. And one way to see why this is so, or how this is kind of matching together, is that like the increase of the function, if viewed from the point of view of its linear approximation. So we will often write in this linear approximation, so that f of okay w, we will often write in that this will be f of w0 plus gradient in w, f of w at the current point. Okay, the current point is w, that's fine. And times the increment. Yeah, so this is W0, right? And the increment is W minus W0. So this amount, by how much the function grows, it should not depend on the change of the coordinates. So if we rescale the units of these weights and keep the function equivalent, then the amount by how much this linear part grows should not depend on the choice of coordinates. And this is what this identity tells us, so that the scalar product equals to the same in the reparameterized coordinates. And then here you see, okay, actually then if W tilde is multiplied by a minus 1, then the gradient has to be multiplied by a, and then they would cancel, and then this would preserve as we wanted. I mean, it's not that we are designing something, but we are now linking together this how these effects work. And then if you do the gradient descent in these reparameterized coordinates, because the gradient differs and because the parameters are defined, are related by this formula, it turns out that if we go change the coordinates, so you remember we had these diagrams. So if we instead of doing this step, we would change the coordinates, do such step, and then map the step back. It turns out that in this space we will be doing like a different step that looks like this, and this is the formula for the step. So when we change the coordinates efficiently, we could say that efficiently we are changing our optimization procedure to scale the gradient with this matrix. So we could speak of, okay, so we actually running a preconditioned gradient descent where each gradient step is transformed by such a matrix. And in the simple case where we like just this, to consider scale in this way, it's up and down. So if the transformed weight is scaled up by the scale s, then the gradient has to be scaled by 1 over s, right? And the effect of the doing gradient descent in this transformed in this scaled space would be to actually have this learning rate scaled by 1 over s squared. And okay, so now one example why this is also like very important and why we don't have actually any reference. So here I was saying, okay, if you do change of the coordinates, then it affects the gradient descent, it changes it like that, so maybe it's bad. But we don't have a reference. We don't know initially are we in this coordinate system or in that coordinate system. So we don't have a way to know in which coordinate system we should actually do this gradient descent. So we just know it changes like this if we change the coordinate system. And like one maybe good illustrative example to pin this down is to observe that if you do some particular rescalings, then it actually defines exactly the same function. So except of the symmetries that we had when permuting the neurons, we have also the symmetry, which is kind of invariance of the network if we do certain changes of the weights here. So what we are doing here, all these weights incoming to the neuron are multiplied by some factor, and all the weights going out of this neuron multiplied by inverse factor. And then if this is a ReLU network, like if this nonlinearity is ReLU, it satisfies this one homogeneity. So if you multiply the ReLU with, hey, what's that? No, this should be the ReLU SX, right, without comma. Yeah, so then the scaling, if it's positive scaling, it goes out of this maximum. And so if you multiply these weights by scale s, then the result is multiplied by the scale s, and then the result after the activation will have a multiple of s, and it will nicely cancel with this blue 1 over s, right? So that's clearly this preserves the function value. So the function, we did a change of weights. They are now different, but the function stayed the same. So we have this invariance of the function to this transform. But the fact from the previous slide still stays. So the gradient of this function in this reparameterized form, it's still related to the gradient of the original function by this ratio. So the derivative of the original weights in the reparameterized weights. So this is going to be like factor of s here and the factor 1 over s. No, rather, how did I say it? So, like, okay, so if w tilde is sw, then the gradient will have factor 1 over s here, right? And like, okay, some basic example to illustrate this. So suppose we have a neural network that has only these 3 neurons, and the weights were equal to 1 initially, and the input maybe was 1, so these ReLU functions here are not saturated. And consider putting there some scaling factors. So okay, so this was like this. So we put here a scaling factor. Yeah, what do we do? So we scale this weight by 10 to the power 2. And this weight we scale by 10 to the power minus 2, right? Then this is equivalent. And then we do the same kind of pair of transforms with this pair of weights, but like this is incoming, outcoming, incoming, outcoming. So these two cancel, right? And here we do the similar pair, but this time this one gets multiplied by 10 to the 2, and this one gets multiplied 10 to the minus 2. Yeah, so this will be equivalent. And here on the right you have this resulting weights, which define the equivalent forward pass. So if you multiply them out, that's still 1, right? So it's equivalent network. But if you compute the gradient in this reparameterized network, so the gradient becomes, so it gets these factors, like 1 over s factors. And yeah, so it's the gradient then looks like this. And you could say, okay, it is highly unbalanced. If we will try to make a step along this direction, we will greatly increase this middle weight, but we will almost do not modify the other weights. So it's kind of like a very unbalanced step in this space, and it can break the optimization. So this is maybe like illustration how it can break the optimization. And what happens here is that you take some neural network, you initialize it with good initialization procedure, maybe Hay initialization, and you then apply some equivalent reparameterizing transform such as this with some large factors as perhaps random. I'm not sure of the details. And that's equivalent network. The activation statistics change, that's true, so they will not be as balanced as with our initial initialization. But the function of the network, so like a kind of the statistics of the output will stay the same. However, the gradients will get rescaled like this, and so if you start doing gradient descent, that will perform poorly. So then this what this plot shows. So actually doing such high reparameterizations can spoil the optimization. So it could be a problem. I mean, we are not sure that our initial solution was necessarily a very good one. Okay, so in this comparison, we know the initial was good one, and we know that we could spoil it, but maybe it's not the best thing that we had initially, and maybe we still have this ambiguity. Okay, in which step we're gonna make the steps, and we know that if this space is chosen wrongly, then it can for surely spoil the optimization. But then what would be a good way to do this? So let's take a look at another example, which is very related to the previous one, but in that case they found that making some random reparameterizations actually improves optimization. So before we had example how it breaks it down, and now example how it improves. And these guys, so we will come back to this setting in a while to see like a good solution. But first also like this other example, they call it neural teleportation. And what they do, so they assign scaling factor to each neuron, and then each weight gets scaled like this. So it's if the weight goes from the neuron A to neuron D, then it is scaled like inverse proportionally to the scale associated to this neuron, and proportionally to the scale associated to the target neuron. Right. So there is this kind of scaling defined for the weights by putting the scales at each neuron. And then they also rescale the activation functions by this law. So if there is the scale factor associated to this neuron, then the input is divided by that scale, and the output of the activation function is multiplied by the very same scale. So if it's a ReLU network, you clearly see this then stays the ReLU activation, right? So then these scales just cancel. And that would be like equivalent reparameterization in the sense of the previous example. So this is kind of generalizes that previous setup to the case of not one homogeneous activation. So you could apply it with the maybe hyperbolic tangent or whatnot activations, or this CELU. So this is in the sense kind of more general way of constructing equivalent networks, but you need to define kind of new activation functions which involve this scaling parameter. In the end of the day, we see that this is actually the same as this generic setup. We just introduced different bases, different choice of weights, different choice of variables. We could make them equivalent to the original choice of the weights, preserving the function value, but then the definition of the function involves the scalings inside, right? So, okay, so this is maybe it is not necessarily to allocate the scales in such a manner, but this is what they did. And you have, as a result, you have this equivalent network just parameterized using the different parameters. And they call such a change a neural teleportation because it kind of creates an equivalent point in the parameter, equivalent network in some sense that has some different properties. And it has what different properties it has? It has like they would run a gradient descent several times and find some local minimum, let's say. And this diagram is one way people are looking to study what is the loss landscape or in the, so okay, so if this is our parameter space and we found 2 points which are local minimum, then we kind of draw such a line in this space and then sample our loss function densely along this line to see how the loss changes if we kind of interpolate between these 2 local minimum or extrapolate beyond them. So these plots are shown in such a slices where the green lines are the local minima, and so here the blue is the loss and the red is accuracy. So here there is a local minimum in the blue, and the local minimum in the blue is some other local minimum. And then, okay, some preceding works were arguing, yeah, you want to have a broad local minima, like a flatter local minima, this will generalize better. But one empirical observation is that if you do these reparameterizations, if you do this rescaling, then this actually changes the sharpness of this local minimum. And then after this equivalent change of basis, this local minima might look like this. So then this is as sharp as the other one. Yeah, so this is one effect. And the other effect is that they were saying, okay, we will start from some good initialization and then do also like this random reparameterization by putting here some random scales at every neuron. And look how the optimization performs starting from this kind of teleported point. And this is the plot showing this. They apply this teleportation at epoch 30 with the different amount of okay, so the scales are random but are in some range, and then you could increase this range, so you kind of get more of the random distortions. And in this case, it was improving the optimization. So the more random distortion of the basis they were introducing, the better the optimization was working as a result. All right, so one solution to this problem that works in this setup when we talk about this equivalent reparameterization. So if this is ReLU or the leaky ReLU, which is one homogeneous, so that you kind of get the same function. And the solution was as follows. They proposed to look, yeah. What maybe I'm missing in this slide is that, you know, the common gradient descent, we discussed this. So it solves the proximal problem, which has the penalty using the Euclidean norm in the space. And then the solution that they were looking for, okay, let's find some kind of norm which will be invariant to these reparameterizations. And the idea here is that if you have any path in this network, such as this green path, then obviously the product of weights along the path will be invariant to any of such equivalent rescalings. So because it will be multiplied by S here once and will get divided by S here. So all these equivalent reparameterizations will cancel out in this product. And so this kind of product is invariant to reparameterizations. And then they say, okay, let's define some distance between in the parameter space from vector W to the vector WT, which will be the difference of these products to some powers, and then consider some overall possible passes. It looks maybe complex, but it's possible to compute using dynamic programming. So it is this product and this sum, they could be distributed, so you could kind of compute sequentially layer by layer. And then I mean, for us, it's important what is the conceptually what's the idea. And the idea is that, okay, so now let's consider this proximal problem where we have this linear approximation to the function, and then using this distance or divergence from the current parameter to the point to the step, to the point after we make the step. And now by design, this distance is invariant, right, to these equivalent transformations. And it happens so that as a result that this step that we are computing, so this scalar product we discussed, this is invariant to reparameterizations. And now we have also like this proximal penalty term, which is also invariant to reparameterization. So this kind of objective is, it looks like it's invariant to any reparameterizations. But as a result of this is that this step that we are computing, it's gonna behave equivariantly with this rescaling with the reparameterizations. So it does not matter what it means, this equivalence is, it does not matter whether we first make a step and then make the transformation, or we first make the transformation and compute the step in the transformed space. Like so, if you had this space and we were doing gradient descent and the trajectory was looking like this, then it would be this trajectory. We could map it, right? So we could map this trajectory into this space, and it would be looking like this. So this is, we've been applying the gradient descent here, gradient descent steps here, and then applying the transform. Or we could be like first applying the transform and doing the gradient descent here. And the equivalence means that we would be actually doing exactly the same sequence, right? So by designing this proximal problem in this way, you are getting the algorithm which is agnostic to particular reparameterization that you apply, so you cannot break it by doing some bad reparameterizations, and so it does not depend on the initial reparameterization, whatever it was. Now, the experimental evidence looks something like this. So if you do stochastic gradient descent with this balanced initialization, it was performing well. If you do unbalanced initialization, so that like you apply some big transformation, then the stochastic gradient descent does not work well, so it's not in this plot. It goes somewhere up. The black sheen is ADA-grad, so some adaptive method. So okay, so this is here with good initialization, and here with unbalanced initialization it still works, but quite poorly. This is test error, so that's, I guess, okay, so it then starts diverging, right, in this sense that the loss starts increasing, or the test error. And this kind of method which is equivalent to the reparameterization, so then this optimizes fast. So this was like a good example for when it performs well. There are some practical limitations. So okay, so this in the form which is written, it is hard to solve for this optimal step, but they found a way how to do efficient approximation to this. So it is kind of almost as cheap to compute as just normal backpropagation, and still with the property that it guarantees equivariance of the updates. It is just maybe not optimal for this formulation, but still has the equivariance property. The other limitation that this is like special for ReLU or leaky ReLU networks. And maybe there are some limitations, I'm not sure about that. If this applies to the residual networks, or does it apply to the networks where you have some things like batch normalization, or perhaps it is not beneficial in practice if you have batch normalization. So anyhow, like, so this is again, one of the methods that has a probably good solution. It was, I think, good. It gives us good insight, but in the end, in the practice, it's not really applied because it has these limitations on the network architecture and maybe some extra complexity in terms of, okay, to implementing this and maybe even in practice, maybe like increasing by a constant factor the computation time. Now, okay, so this was a solution, but principled one for this specific problem. If it was a one homogeneous network activation function network with one homogeneous activation functions. There is also a principled solution for quite general case, and I like to show it to you. It's again, it's not gonna be immediately practical and very useful, but at least. Mm-hmm.
I see relations to initializations, to batch norm,
Mm-hmm.
and you said like in practice we just use the initialization or batch norm like much more often because of some of the limitations of this. But so what would be main positive message for this method then? Like the biggest inside or?
Yeah, to me, like this is absolutely not clear. I mean, what we have is that we know there is this issue, and the common stochastic gradient descent is sensitive to that. It could spoil the optimization. Sometimes it could improve the optimization if you play with in this space of the reparameterizations. And here is the principal solution, how you do it in the way that it is equivalent to the reparameterization. So you can be guaranteed to be robust, and it works well in this example. So it looks like it's a great method. But then, yes, what I don't know is that, okay, does it keep this advantage if you look at the competitors like Adam, and we have network with batch norm and so on? Maybe not. So yeah, so here I don't know.
It's quite an old method, relatively old method, and we don't have probably results like trying it like on some model.
Large models, yes, also, yeah. Yes. So the general solution, it's constructed along the same lines. Like we want to have a proximal term which is invariant to any kind of reparameterizations. And it's nice in the following statistical setup. So if you have a probabilistic predictor for, okay, let's say we are doing this conditional prediction, and the loss function is the negative likelihood that what we are minimizing, so like expected negative likelihood of the predictions. Then we can construct the following proximal problem. So this is our linear approximation to the loss function. And here we measure like deviation between the current point and the point after the step. And the proposal here is to measure this deviation actually by the distribution on, divergence of how this distribution changes as the result of the step. So the key idea is that if your predictive probabilities do not change with respect to some reparameterizations or whatever, then the probability distribution does not change, and then this measure will not change. So this is going to be invariant by design to any possible kind of moves in this space of the parameters, linear or non-linear, such that if this change of the parameters preserves the predictive probability distribution, the function that we care about, then this divergence will be invariant to that. So we only care about changes in the parameter space so long as they do affect our predictive model. So Yeah, and Kullback-Leibler divergence is, yeah, so is one measure of distances between distributions, if you like. No, it's not distance because it's not symmetric, but yeah, it's divergence in the sense that the distributions matching if and only if this divergence is zero, and it's convex in the first argument for every second argument, or the other way around. So rather the other way around. So it's convex in this second argument for every first argument. Or maybe both. Okay, yeah, so that's invariant, and this is like our nice design. And furthermore, if we consider, so here we have this factor which controls, in the end will control our step size. So, and this factor controls, okay, how do we weight this linear approximation or improvement in the linear approximation versus the deviation in the parameter space. And if we set this alpha very small, this will correspond to small step sizes, so that this will be kind of, this penalty will be amplified and the step size will be smaller. And what happens in the limit of small step sizes, then this divergence we could approximate locally using its second order Taylor expansion. So, and it turns out that this local approximation, it is going to be a quadratic form with the quadratic matrix being the Fisher information matrix of this probabilistic predictor. And this Fisher information matrix is something, okay, in this case we have this look, we have this expectation over the inputs as well. So this, we have divergence over these labels y, but we have also the expectation over the inputs x. So we have this kind of expected Fisher information matrix, this expectation over the true data, but then there is the expectation over the labels drawn from our predictive model. And then there is basically the gradient of the loss, the log probability. And this tensor product means like outer product. So we have a gradient. Yeah, okay, what it's supposed to mean, I mean, it should be vector time column vector times the row vector. So this should be some like outer product matrix, right? Like what we often denote as AAT, right? So this kind of matrix. So the outer product of two vectors. But here derivative is mistakenly a row vector. So that's okay, but maybe this notation still could be applied to that. Yeah, so then this is the area. Okay, so if you have such a matrix, then you could make a step, the optimal step, using this quadratic approximation here, and the optimal step then can be computed in closed form, and it turns out to be this. So this matrix will be, you need to multiply the gradient of your loss by the inverse of this matrix. So this is quite similar to maybe Newton methods, right? Also for these Gauss-Newton methods, there will be some matrix that contains some kind of second order information about our loss function, and then we need to rescale the gradient by multiplying with this inverse. So here it is this Fisher information matrix, and this is like, okay, so we got it by design from saying that we're going to make a proximal step that cares only about the divergence in our predictive distributions. And this is called natural gradient descent, or the natural gradient method. So doing these steps. And these steps by design, so they are going to be equivalent to any nonlinear transforms. No, sorry. So will be equivalent to any linear transforms. This part would still be invariant to any nonlinear transforms, but the gradient does not. So if you do nonlinear transforms, also this gradient, the local improvement, no, it works. Sorry for confusion. Yeah, I think it will work also for the nonlinear transforms, because the approximation of the function will still work locally. So it would be kind of if the step sizes are small enough, it does not matter how linearly or non-linearly we reparameterize our loss function. So it would kind of optimize it the same way. And not only it is achieving this equivalence to all these reparameterizations, it is also in some sense good optimization directions. So it can be shown that for quadratic functions it will be doing what we want, and so on. So this is like theoretically maybe great solution for the problem, but it's hard to implement. Even despite here we only need derivatives of this log likelihood, which we kind of already doing for our training data, but here we need them for random classes sampled from the model, not from the data set, but from the model. And we have to, maybe the most main difficulty is that we have to deal somehow with this matrix. So we cannot like store such a matrix for neural networks because it has the quadratic size in the number of parameters. And we cannot really invert it, right? So any approximation would need to be something computationally tractable, like a low rank approximation to this matrix, or diagonal plus low rank, and this kind of approximations. They've been developed, so there are methods. But again, so this is not going to be the mainstream because this likely involves more computations, likely involves some approximations, and then I guess it's up to practice. So if in the practice some methods are fast and give you satisfactory results, then you probably will not be bothering to implement the difficult ones and spend more time on executing them and to even check whether they would be better.
So does the metric needs to be really big? Like, okay, it may not be exact, but if you just like, there's this expected value, you can compute it through some small batch.
Yeah, the expectations not a problem. So yes, we could make like a stochastic estimation.
You say the metric is big?
Yeah, it is. You see, it's like.
I imagine taking a single sample, like really like doing wild.
But
something like that. Like, where does the size comes from? Like,
the size comes from this outer product. So for every point that you sample, you can compute the gradient, and this is, say, n parameters. But then you need to form this outer product of this gradient with itself. And then you need to sum many such matrices. Like when you compute...
the size of the parameters squared, okay.
Yeah, when you compute this...
Okay, it's not depending on the sample, I see.
Yeah. When you compute the sample covariance matrix, it's like, yes, so the number of coordinates times number of coordinates, and it's sum of such outer products. It's similar in that sense. And yeah, and then okay, but I mean the takeaway from this is that yes, so if we carefully design this proximal problem such that we have a very sensible divergence here, which is invariant to all the possible representations, that we are getting some kind of statistically optimal gradient descent algorithm, but practically we cannot realize that, right? And then maybe it will be, there could be some additional difficulties in the stochastic setting and so on. So if this matrix is estimated only from some mini batch, yeah, so it could be, it could this could quite easily spoil this.
Can you see this divergence term, like seeing this kind of some sort of regularization, right? Or just like saying like I don't want to change my result too fast or something like that.
Yes, exactly. As in any of these proximal problems, we are adding some penalty on the deviation from our current parameter value, but then we can measure this deviation using different divergences or metrics or distances. We could use L2 distance, and then this we were using LP distance, and it was having different effects. We could use this Kolbe-Kleiber divergence, which has this plus of being invariant to any reparameterizations, and like we could arguably say that this is what we care about.
This is where I'm starting. Yeah, like okay, this is like a plus. Like why would you use it?
Mm-hmm.
But I'm struggling like to understand the motivation line, why this is a good regularization. I mean, maybe yes, because it's like usually we have regularization on the parameters themselves, like something, yeah. And here you say I have regularization on the output layer, and
Well,
at the beginning I would say like let's go fast, yeah, but you say.
this is not to be confused with the regularization really, because it's like, okay, so it is a penalty on the deviation. So if you are here and have some gradient here, it is some kind of penalty on the step that we are adding here, so not to step too far. And this penalty becomes high if we see that the predictive probability distribution changes a lot. And then we make a step, and then we are in the new point. So then this penalty will be then reapplied in the new point. It's not the penalty on the parameter values themselves, it's the penalty on this step. Like how far we are hoping to go, knowing this linear approximation and our model in this case. So it kind of it is a lot of calculations, right? But it extracts a lot of information from the model, namely its local curvature kind of properties. Okay. So, I mean, to summarize, so we've seen that this reparameterizations is a big deal, so they could spoil the training or sometimes improve the training, and we could design invariant methods, sometimes practical, but maybe limited, sometimes even like theoretically optimal in some sense, but maybe even more practically limiting. And now, like the last section, last part of the talk is to talk about these practical approaches, which I think they arise from the idea of doing some kind of normalization. And this normalization, I like to explain it from the point of view of replacing these proximal problems with the trust region problems. So we had also we already had in the in this adversarial lecture this kind of trust region problem that you are saying, okay, we have our linear approximation here, but we are not going to add the penalty, but we're going to put a hard constraint that some norm of the displacement must be strictly reasonable. So instead of this penalty function, we are going to like maybe we have some metric, and then we threshold this metric at some value, and this defines us some interval. Okay, and the question is that what is the best parameter value in this interval or the disk, where the linear function is minimized. So, right. So in this case, in this point. Yeah. So if you solve that, it turns out that the solution is given by dividing the gradient by this respective norm. So if the gradient was this blue one, in this case, the normal gradient descent would like shoot the full length of the gradient. But if we solving this trust region problem, we are going, so we divide the gradient by this norm and multiplying with this epsilon. So in fact, we are going in the direction of the true gradient, but the length of the step is not controlled by the gradient anymore. It's controlled purely by this fixed parameter. So it's going to be like fixed length step in the direction of the gradient. And yeah, so this type of steps arising from such trust region problems, I call normalized steps, because we are normalizing by the magnitude of the gradient, or some value like associated to the magnitude of the gradient. And now let's see what it is doing in terms of if we change the basis. So what happens to this type of methods if we change the basis? Then okay, so this is example. So let's scale the x by some scaling factor s. Then the gradient scales is 1 over s, and the step size defined as this normalized reparameterized gradient. So what happens? It stays. So it will be the same step in this original and reparameterized space. And then in the original space, so if you do it in the reparameterized space and then scale it back to the original space, we see that it scales as 1 over s. So for the common gradient descent, we had this relation that the delta x would be like so we had the relation that there would be 1 over s squared. So there was some epsilon times the gradient, right? No, yeah, so something like this. So this was the SG common gradient descent. Now with this normalized rule, we are getting that if we do the step in the reparameterized space and then interpret it back in the original space, we are going this 1 over s rule. So here we have this factor 1 over s squared. Here it's 1 over s, so it's kind of better in that regard. So it is not as strong dependence, so is not as big changes if you change the scale. So we could say that it is kind of more moderate dependence on the change of the reparameterization, but it's still there. So it is not equivalent to the change of the scale. So if you change the scale, these normalized methods will change. So their behavior will change. So this teleportation and all other things will have effect on this normalized methods as well. We could have achieved the equivalence to this rescaling by dividing by not by the norm of the gradient, but by the square norm of the gradient. Yeah, so this will like eat up the whole s squared. So this would be actually equivalent, but other than that, it's maybe not a good step in any of the reparameterized spaces. So it's not only the equivalence that we want to achieve, we also want to achieve good optimization somehow, which is like more difficult to capture formally. But yeah, it turns out that if we divide by the square, we are not achieving good optimization. So that's not working. And dividing by the norm is kind of okay. So something in between, maybe not as sensitive to the change of reparameterization. Yeah, so and then as you've seen in the natural gradient case, so that actually multiply it with some inverse matrix, which contains the second order information, the curvature is equivalent to the scale. So all the methods like Newton method or the Gauss-Newton would have this equivalence, but they would not necessarily be good for this our nonlinear optimization, and especially they would be difficult to compute in this case, like more harder to compute. So the Newton method would not be good because it's not convex optimization, right? We have this positive and negative eigenvalues of this Hessian. The Gauss-Newton method would be good, but like okay, hard to compute. So that was one aspect of this normalized step, which we discussed that had to deal with these equivalences. The other aspect is that it turns out it is actually maybe rather suitable for nonlinear optimization. And to discuss about this, I have this comparison, like, okay, kind of pros and cons for stepping proportionally to the length of the gradient versus stepping just in the direction of the gradient with the constant step size. And much of the motivation for stepping with the length of the gradient is associated to convex optimization. In particular, in the convex optimization, if the function is strictly convex, it holds that the further you are from the optimum, the larger is the gradient. So for quadratic functions, this is like quite obvious, but it's also in general for all convex functions. So if there has some parameter which controls how strictly it is convex, then it turns out there is this relation that between the norm of the gradient and how far you are from the optimum in the space of the parameters. This is one inequality. The other inequality in the value of the function. So if you're far in the value of the function, then that means you are also far in the parameter space, and it means the gradient is higher. So if you are far, then your optimal strategy then would be to make a larger step in some sense. So this allows, in the convex setup, it allows much faster theoretical convergence guarantees for many methods and so on. And then you don't even need to be monotonous to achieve convergence in the function of the value. So it's enough that you are stepping towards the optimal solution. So things like that. Right. In the non-convex case, non-linear case, it could be quite different. So there is no kind of global relation between the gradient and the shape of the function where the global optimum is and so on. So it's very local information that we have. And it could be for quite well the case that the gradient is small, but you are on some plateau which is far away from the global minimum. So actually what you would want to do here is to make some not too small steps, such as not to get stuck in this plateau and still to move somewhere. Or the opposite situation could be the gradient is very high, but this is like a sharp minimum. Then you want to be careful and not to make the step proportional to this high gradient, which would be too big to overshoot out of this global minimum and sort of diverge if you are stepping proportionally to the gradient. So then in this setup, it is maybe rather intuitive that, okay, you could be doing quite well actually if you are going in the direction of the gradient, but you are not using its length, but just the direction, and make the steps of constant length in that direction. So this is kind of example on the fingers, but I think it conveys some intuition and triggers some thinking for what the information is contained in the length of the gradient and how we're gonna use that. Now, yeah, so finally coming to these practical methods like Adam-like methods, the interpretation that I would propose you is the following. So we've discussed this type of trust region, so dividing by the length. Now we could also consider these box trust regions, which penalizes the maximum deviation among the coordinates, or restricts the maximum coordination over the coordinates. And in this case, this proximal step problem decouples, and similarly to this first sun gradient attack, we are getting the solution that, okay, along each coordinate, we need to step in the direction of the gradient along that coordinate. So it means like using the sign of the gradient for that coordination, for that coordinate. So that would be like a very simple recipe and easy to implement in practice as well. There is one caveat with these normalizations, and the caveat, what we have not discussed, I mean what is not covered in this picture, is that we are doing stochastic optimization. And with stochastic optimization, if we are doing some kind of very nonlinear transform of the gradient, it could break down the optimization. So this was one example which was proven by in one paper that came after Adam to show that the Adam may fail to converge. So okay, empirically it was working well, but theoretically maybe some people tried to prove that it converges, maybe they could not, and then somebody proved, okay, actually they show the counterexample that it might be divergent even for some simple functions. It would be failing to optimize this in the stochastic setting. And the counterexample is essentially this, so that you have a loss function which is a sum of these three linear functions, so these two blue functions and one red function. So in the total, the loss function is linear and has the negative slope like this, right? No. Yeah, so the slopes are indicated here by these numbers. Graphically, that's incorrect. So if you do the -3 and 1, 1, this totals to the opposite direction, right? So the total function is this with the slope -1, right? So if you are doing the correct steps, minimizing this function, we should be going in that direction. But what happens in the stochastic setting, if there are these two blue functions with the small slope, but only one with the high slope, that like on average, if you draw them at random and make this normalized step, like in the according to the sign of the gradient, so here we will be doing these steps, but twice as often then we will be doing the red step, and then this on average we will be going left. So that's not good. And yeah, so this happens because we normalized here by the gradient of this stochastically sampled function, and that's not good. So the kind of fix to that is to, instead of normalizing by the gradient of the current stochastically sampled function, we would want to normalize by the expected kind of norm of the expected gradient. And then we would be rather in this setting, and then we would be fine. So if we here we were moving using the stochastic gradient even, but normalizing by the norm of the expected gradient, it would be fine, because then like it will be kind of the step will be proportional to this actually stochastically measured value, but they will have all the common denominator, and then they will average out, and it will be moving in the right direction. So what this means in practice? It means that we need to divide by something which is averages over the past batches. So this is how we approximate the expectations of our rollers. This gives us this following recipes, which are the different variants of like normalized gradient descent steps. They are quite similar in that you have estimate of the gradient in the numerator. In this case, it is the current stochastic gradient in the numerator. In this case, also current stochastic gradient in the numerator. In this case, the filtered gradient, as we discussed in SGD lecture. You can use the past iterates to reduce the variance of your gradient direction. So this is sort of exponentially weighted average of the gradient, or gradient with momentum, if you like. But yeah, anyhow, like gradient, and the numerator is some kind of norm of the average of also like a filter of all the stochastic gradients that you measured in the past. So in this case, it is kind of flat mean average. So you take the gradients from all the past iterations, they square them, and then you compute the flat running mean over all of the past iterations, and then the square root. So this is this kind of normalization. Here it is the exponentially weighted average with the stochastic gradient, and finally in Adam it is this exponentially weighted average, and then in the numerator exponentially weighted average squared gradients, right? So they differ kind of in these filterings. And we discussed now, okay, in the numerator we want a filter which is kind of not changing too fast as to prevent this convergence properties. So the numerator should be changing slow, and in practice this is achieved by using here the filter which is sort of averages over more of the past iterations. So this is achieved by this exponentially weighted average with this momentum coefficient, if you like, of this quite large value by default. And in the numerator, there is this trade-off, which is between having this accumulated inertia term, which could be harmful because we are using the gradient estimates from the past and not the current ones, and between the variance. So default here is then significantly smaller value, which is sort of much closer to the current stochastic estimates. All right, what else to mention? Yeah, here there are these step sizes, which is 1 over the square root. This is because in that paper the algorithm was introduced with the convergence guarantees, and that was necessary. The other methods, they were not proven convergence guarantees, and this was like a practically, empirically proposed things. So they did not, like, they put the constant learning rates here. I guess, okay, so maybe in this paper that was discussing what is the counterexample, and then the kind of the fix for that, if you need either a flat averaging or other kind of averaging which is not as sensitive, so it does not vary as fast. So then the convergence can be shown, and then again for the convergence there would be needed 1 over the square root of t. So we could kind of neglect this in practice. So
we sort of use these schedulers not exactly
Yeah.
square root of t, but it's also like decreasing, so maybe.
Yeah, in practice we have these schedules which are decreasing much faster to have this training stabilize at something. But it's not exactly the same as to convergence to the local optima of this stochastic loss, right? Yeah, okay, so some summary about this. So some of these normalizations, they were empirically proposed. And here is the trade-off is that the gain is that we are partially robust to the reparameterizations. And it pays off, so you could see the examples how these optimizations work on some difficult non-convex functions with maybe level sets curved and flat like this, so they work more adaptively and better than the gradient descent, which would be kind of zigzagging here and getting stuck. So this method would be working better. How exactly what is the norm here is taken exactly why it is the square root of this exponentially weighted average of the squares. This is empirical. So this one on one side people are trying to explain it as a kind of approximate second order methods. This doesn't work because the true second method would not have the square root. Or you could view it as this normalization kind of approach that I've discussed. It's also like, yeah, it depends like what kind of norm you are computing here and whether, so this is not really a norm, what is here, because it's average of the second moments rather than the norm of the average gradient. I guess the norm of the average gradient could also be tried and see how that works in practice. So these details are kind of up to practice. But what we know, I mean, what is our takeaway is that we know that these reparameterizations, so these spurious degrees of freedom in the parameter space, they are important and could be important for initialization and for performance of the optimization. So this is one thing. We have ways to address that. And yeah, so these adaptive methods partially address that while also being cheap. I guess this is sort of the state of the arts. Okay, that's all. Thank you.